All right, welcome to the end of week 3, and as per tradition, at the end of the week, they release a brand new question. So this question is, we're given a binary matrix, and we want to find the first column that contains a 1 in any of the rows. So here's column 0, column 1, there is no 1 anywhere, so we return -1. And a more complicated example, we return column. So this is column 0, column 1. We return column 1 because this is the first column with a 1 in any of its rows. Okay, so they also say something about the fact that we're not allowed to make more than 1,000 calls to get, an element from our matrix. And also that our matrix will be within the bounds of 100 times 100. And that it's sorted in a non-decreasing way. So we see a bunch of zeros and then we see a bunch of ones if there's any ones. Okay, so I copied down the constraint down here, and let's think about some solutions. So first we have the brute force. For every row, look at every column to find the first one with a 1, and then we just update our best solution if it's better. So that means for every row, so let's say we have n rows and m columns, we are scanning through m of its columns. So for a matrix like 100 times 100, we're going to be making 10,000 calls, which is a lot greater than the 1,000 that were allotted. So brute force is not fast enough. So the other solution we have is we can walk from top right to bottom left. And the intuition with this solution is, so we scan through and we find that our best solution so far is at this index here, so column 3. Then for the next row, there's no reason to search for a possibly worse solution of anything there. So we can cut our search by starting at this column instead. So if there was a better solution, it would be at 2 or lower. So we no longer need to search for column 3. So we kind of do like a zigzag down. And then here we find that our best solution is at 1. So that means if we have a better solution, it's to the left of it. So when we come down to row 2 and we see that it's a 0, then that means this row does not have a better solution for us. So we can just skip it. So we can just go straight down. If there was a third column here, we can go straight down and then continue our search. So this is kind of like a zigzag. So you always you're always going either left or you're going down. So that means at most, we're walking n plus m. So we're walking through all the rows and we're walking through all the columns, but we're not duplicating anywhere. So that means for a matrix of 100 times 100, so what I meant is like we only look at every row and every column at most once. It's only 100 plus 100, which is, this is a lot better, and it's within our constraint. So the third solution I want to talk about is binary search, but we'll come back to that in a little bit after we've coded this solution. Okay, so first let's get our dimensions. And then we want to get our rows, which will be at the 0th index, and our columns, which will be at the first index. Okay, so now we have some sort of our best solution so far. We'll set it to something that's impossible. So we can't have a column index of columns length. And here we can return if leftmost is equal to columns, then we can return -1. Otherwise, we can return leftmost. Okay, so now we want to go through our rows. So for int I, int row, and we also want to keep track of which column we're on. So let's have our column here. Okay, so what we want to do is we want to find this boundary where we see a bunch of 1s and then we finally see a 0. So what we want to do is we'll have some sort of a while loop, and while binary matrix dot get at this row, so we look ahead, equals 1, we can continue. So we can do column minus minus. So if we see something like this, so if we're if we're here and we peek ahead and it's still a 1, then that means this is not our solution. So we move to the next column. However, we want to make sure that if column is equal to 0, then this is our solution. This is return 0. We found the best solution we could ever find. We found a 1 in the very first column. And this prevents us from indexing into a negative here. Okay, so now if column is less than our leftmost, then we can replace leftmost with a better solution that we found. And you can see because column is on the outside, when we come into another row, we'll keep our best solution that we found so far. Okay, so that should be that. We'll try submitting if there's no compile errors. Cool. So this, as we said before, has a runtime of O of n plus n. But let's imagine a case where we see something like this. We see 0, a bunch of 1s, and then maybe a bunch of 1s here. So with this approach of walking, we would start, from here, and then we'd start walking through to find this point is here. So here we've probed all of these points. Now, is there a way to utilize binary search so that we can jump to that point faster? And the answer is of course yes. So we have in our binary search we have a left window and a right window, and we just probe the middle here. Now this middle tells us here we have 1 1, so that means our solution must be somewhere on this side. Here we have 0, so if this is a 0, then our solution is probably somewhere here, and then we keep jumping, and now we finally found our solution. So you can see here, if this length has a length of, I guess, m, then this is O of log m, whereas, in this version, we did a O of m search to find our first index. Okay, so this, will have some sort of a runtime of n rows of log m columns at each time. And you can see here that, there is a trade-off between when 1 is good and 1 is worse. And we'll go over that at the very end, but first, let's just implement this and see what it looks like. So here, instead of columns, we're going to have some sort of a window. So we have our left window, and we have our right window. And this right window is going to be, I guess, also columns minus 1. So it's at the very end. But if we found a better leftmost, so if leftmost is smaller than right, then we can update our rightmost window to leftmost minus 1. So this is the same idea as here. If we found that our solution is this, so for the first row, our solution is this, then for the second row, when we're scanning here, we don't need to start with our window at the very end. We can cut our window just to here, because if there was a better solution, it would be in this subarray. Okay, so now we have that. So there we have our left and right window. And then what we want to do is, while left is less than or equal to right, let's probe the middle. So we'll have int middle equal to left plus right minus left divided by 2. I like to do my middle calculation this way because it prevents us from having a integer overflow. If we do something like left plus right, if these are two very big numbers, we'd have an overflow. That case won't happen here because of our constraints, but that's what I'm being accustomed to. Okay, so let's probe our middle bit. It's going to be equal to binary matrix dot get at this row at our middle bit. So there's a couple of cases here. If middle bit is equal to 0, then our solution must be somewhere on the right side. So our solution will be somewhere on the right side. We'll do start is equal to middle plus 1 to move there. Okay, so what about some other cases? So here, our middle bit is equal to 1. If middle is equal to the first column, then we can return 0. So this is the same case as here. If it's the first column, then we're done. So now it's not in the first column, means that we have to try and search for whether or not we probed here or we probed the correct, or we probed the correct spot. Okay, so let's see. We have to look at the previous bit. So here, remember, we don't know if we saw this bit or this bit. So let's probe the previous bit. We have int previous bit is equal to binary matrix dot get this row at this middle minus 1. Now if previous bit is equal to 0, then this is the solution for this row. So let's keep track of that somehow. We have our best column, column for this row. It will be equal to, columns. So something that's not possible. And then here we finally found our solution. So column will be equal to middle. So we can break out of it. Okay, otherwise, we found a case where we're here, 1, and our previous bit is still a 1. So that means our solution must be on the left side. So here we'll want to update our end to be equal to middle minus 1. So if, for example, we probed here, then now we can update our index and search this subarray instead. Okay. So that should be good to go. Actually, one more case we want to do here is we can actually do a very cheap test for our right. So, int right bit equal binary matrix dot get this row at right. If right bit is equal to 0, then there is no better solution. We can just continue. So we do a check for the right bit before executing our binary search. Because if it's 0, then there's no better solution. Okay, let's give this one a go again, assuming that I wrote everything correctly. Oh, let's see, 77. And, right, so this is not the end, this is called right. And, and I guess this is called left. Sorry about that. Left and right. Okay, we'll try submitting it. And then if this works, I'll go over some cases of where the binary search, let's see, something happened. We have our left, we have our right. If we have a better leftmost, then we can shorten our window. Okay, row right, start at the end, right minus left divided by 2, get our middle bit, and if it's 0, then we can shift to the right, okay? If our middle is 0, then we return 0, and then we get our previous bit here. If the previous bit is equal to 0, then column is equal to middle, and we can break. Right, forgot about this. So here we want to go if column is less than leftmost, then leftmost is equal to column. Accidentally deleted that. Okay, let's submit. Cool, so now it's accepted. So the case I want to go over is, why would O of n log m be better at O of n plus m in some cases? And it basically boils down to, so we have our binary search and we'll have our walk. Basically boils down to when one is a lot bigger than the other. So, if we assume that m is a lot bigger than n, then this roughly becomes O of m. But this just becomes O of n, and if we log m it, it's going to become a much smaller number. So it's going to be O of n log m, and this is going to be smaller than O of m. So let's do a concrete example. Let's say we have 100 columns and we have four rows. So worst case, with our walk, we're going to do 104 steps. But what about in our binary search? Well, we're going to do, let's say worst case, we'll do something like log of 100 plus log of 99 plus log of 98 plus log of 97. So one for each row. And and each time we do binary search, we found it on our rightmost index. So what does this equal? This is going to be equal to, roughly here, 33. So that means, binary search, we only probe 33 times. Walk, we had to do at worst 104 times. So that's when, there is a certain trade-off there. Okay, that's the end of today, and I'll see you on the next one.